What I'm going to attempt to do today is give you a picture, an overview of the kind of R&D we do at GE. And we're a big place, and so I'm going to be going through this pretty fast, but I am perfectly willing to be interrupted at any point if someone has an appropriate question, and I'll try to leave some time at the end for that. Find the proper device. Yes. These are the businesses within GE. GE is the largest industrial conglomerate in the world, and so has a number of different business areas which change. GE buys and sells companies, and most recently, GE decided to go out of the banking business, I'll call it, just to use a simple word. GE Capital is being disbanded now. Most of it has gone, and they've replaced it with a new business that has just been created within the company called GE Digital, which replaces, well, actually emphasizes the role of computing and software in current modern industrial work. I'll say more about that later. The other businesses, power and water. This is generating the electricity that all of us use on the grid. This is the grid itself. This is a lot of work that we do in the healthcare area, aviation, jet engines. We are the largest builder of locomotives on the planet. This is the lighting business. Although there are a lot of other things that take place within these, I'm going to stop at the description there just to give you a little familiarity of what we're doing. We just bought the largest acquisition in GE's history. We bought the largest electrical company in France called Alstom, which has now been integrated into the businesses that I just showed you within GE. And that's just a picture of where the locations are in Alstom. So that's just the additions from Alstom into GE's businesses and their locations. So GE is very global indeed. We like to say that one of the biggest inventions that Edison actually did, our founder, is that he invented the Industrial Research Lab in the United States. We do what we call market-focused R&D. You would say that's applied research. That's the main objective of the R&D within GE. Not that we don't have some basic problems that have to be solved, but that's the focus. And GE has about 50,000 engineers in the company. And so all of those get linked together through global research. These are locations that we have for just GE Global Research, not the business locations, but this is GE Global Research itself. I'm from the main location, the original location, which is in New York, which is a suburb of Albany, New York, upstate New York. We have been adding other locations in the last 20 years. The reason for this, of course, is that R&D is developing well in other countries. The US is not the place where everyone immigrates these days to do R&D in science. It's taking place well in many other countries. The developing countries are developing. And so to take advantage of that brain power, of that work, we need locations other than in the US. And so we have a location in Bangalore, India, Shanghai, China, Munich, Germany. These are in the order they were created. And we have an advanced manufacturing center in Detroit that we've put in recently, and we've put in one in Rio de Janeiro in Brazil. This is a software center in San Ramon, California. Tiat Carmel in Israel has a technology center as well. Oil and gas technology center centered on that business is in Oklahoma City. And then we just put one in Dhahran, Saudi Arabia. And there are also a couple of, let's say, listening posts in Moscow, Tokyo, and Seoul. So it's definitely a global enterprise, and the nature of R&D in the world makes that necessary. It's also very true that we do a lot of collaborations, and this is just a general picture of what goes on. GE spends over $5 billion a year on R&D every year, which is a lot, but that's way less than 1% of the world's R&D every year. And so if we don't pay attention to what everyone else is doing, we're going to miss very important things. We're not going to invent all the important things, even for GE ourselves. We have to collaborate. We have to talk to others. I think that's true of anyone working in science and engineering these days. It's the nature of our enterprise that it's global, and just getting more so. Of course, we work with you guys. As Peter has just told us, GE has a lot of work we have done with your very nice APS here, your light source. We also have made great use of your HPC cluster, your high performance computing cluster here. We've used that a lot. So those are two areas that I'm instantly familiar with. Thank you very much. We've made good use of Argonne Lab. Thank you, Peter, and thank you everyone in the room for the help. We need it in the global environment in which we need to compete and operate. Okay, now I'm going to go a little bit more into the GE businesses and show you the kinds of things we do for them. This is the aviation business. Of course, we make jet engines, and they're complex devices. As it says here, there are 15,000 parts in a jet engine, basically. What this has been is a platform for science and engineering development, because it's always trying to tear itself up. Whenever we make an engine, everyone wants a better engine. And the temperatures go up in the engine, the forces go up in the engine. They'll wreck any material that you can put into them over time. And so you have to be very careful with what you put into them. Naturally, all of us who fly want everyone to be very careful who does this business. What's interesting lately in this area is that we're using materials, beginning to use materials that have never been used before in a machine of this type. Ceramics, of course, have been in use in engineering and science a long time, but never in machines like this. As you know, metals have ductility, and we understand fracture in those materials well. Ceramics, although they're very nice from the standpoint of temperature maintenance with them, they're not very good from the point of view of breakage, fracture toughness. And so no one's ever thought of putting them really in these machines, but we've been trying, and now we're finally succeeding. We're actually putting ceramics into certain parts of the jet engines. And this has been a very long process. I'm not going to read this to you or go into that kind of detail. The point being, which I think you guys know, is that materials development, fundamental materials development, carrying it from fundamental knowledge about the material to actually using it, is a very long process. So this is the sketch of the 25 years roughly GE has been working on ceramics to make them eligible for putting in a machine like a jet engine. And we started around 1990, and it's just getting into planes now. As a matter of fact, it's actually being flown now in some jet engines that have just come out this year. This is another area of a lot of interest in the aviation business, but also all of our other businesses, because we manufacture a lot of different things in those businesses. Additive manufacturing is a big theme. Of course, the traditional way of manufacturing a part has been to make a bulk piece of material that may resemble that part, and then you machine out the part that you like from it. That's subtractive manufacturing, the standard method. In this particular method, you take powder of the material that you're interested in making into the part. Under computer control, you direct lasers onto the powder stream and build the part from a powder stream. And as you can imagine, there are a lot of questions relative to the traditional way of doing things that this would engender. So solving those questions is a big effort in GE and a lot of other places. We're looking at the benefits that you can get. Additive manufacturing can reduce the energy by 50% of making parts and reduce material wastage by up to 90%. So there's a lot to be gained if you can do this. But as you might suspect, when you put materials together this way, the properties are different than if you use the standard techniques of forging or whatever you would have used initially. So we're paying a lot of attention to those properties. And there's a lot of work we're doing here with you guys on the APS relate to this particular question that's arisen in additive manufacturing. But we are using it now. It's actually eligible for making parts. Particular engine, the LEAP is the name of the latest engine that we've been building, latest jet engine. And we're building the fuel nozzles in that engine now with additive manufacturing, and we're finding that we can get 5 times the durability of the fuel nozzles with less weight, and weight reduction is always an objective when you're flying things. And we're building 18 to 19 fuel nozzles for each engine. And we think we're going to be building for engines 100,000 parts by 2020 by additive manufacturing. The facility for this is in Auburn, Alabama, as it says. And it's flying. Those engines were delivered just this year for these particular planes, and those ceramics that I showed you and those additive parts are in that plane. So it's working. Getting onto some other businesses, the power and the water business, that's where we make our large turbines for generating electric power. A lot of work there concerns combustion techniques, coatings for protecting the parts from the high temperatures in the machines, fuel flexibility. People would like to burn different types of fuels in the machine, a lot of work in that area. The healthcare business, we do work in molecular diagnostics area. GE sells techniques and equipment for molecular diagnostics, and we sell it to pharmaceutical companies who actually produce biological materials using equipment that we sell that eventually become pharmaceutical agents. Decisioning technologies, this is a software area. We're trying to help hospitals handle loads that they have and become more efficient. And of course, we have a lot of diagnostic equipment, X-ray machines, MRI, nuclear medicine machines that we are continuously trying to improve. This shows the latest turbine that's called the HA, that's the name of it, that we've built in the power business. It now has the world record for efficiency of a power plant. In a combined cycle power plant, it produced about 61% total overall efficiency of the plant in combined cycle. This is the latest particular one we have built. As you can imagine, there is a lot of cross-referencing between the techniques in this business and the aviation business because the turbines have a lot of similarities. There are a lot of differences too. They don't pay much attention to weight in this business. They pay a lot of attention to it in the aviation business. But a lot of knowledge goes back and forth between those businesses. You may not know that GE is a large water company. I don't know that we're the largest, but we're certainly one of the largest in the US. We supply a lot of techniques for cleaning up water to industrial users like oil and gas industry, who has a lot of cleanup problems with water that they need to deal with. We sell desalination equipment for ocean water all over the planet. And then we tackle very, very clean water problems, for instance, in chip fabs, where you have to have extremely clean water, or the water that you put into a nuclear reactor has to be extremely clean. So we supply the techniques for that sort of extreme cleanup on water as well. So I'm not going to read those. Those are the kinds of things that we sell in that particular business. Oil and gas business, I'll show a little more about this in a moment, but we do build a lot of equipment for that industry. We are not in the oil and gas exploration business, or we don't make any fuels or any oil and gas for selling that, but we sell a lot of equipment to those industries to help them with their job. And I'll show some more about that in another. It mentions water treatment here for them, which I did just talk about. The transportation business, we are in the locomotive business. We're the largest maker of locomotives in the world, and we pay a lot of attention to emission requirements there. We also make a lot of hybrid electric platforms for extremely large transportation vehicles, like over the off-road mining vehicles, for instance, which are huge. That's a picture of one of the difficult areas where we work and supply equipment. All the easy oil has basically been found, so the companies that search for it are going to more and more difficult places. One of the places that they go is down on the ocean bottom, and I'm talking about like, a mile down. And so they want us to bring them a lot of equipment for pumps and motors and things like that. And and blowout protectors. That's the thing that failed in the Gulf. That wasn't ours, thank goodness. But it can cause great problems, of course, when these things don't work. We do supply that stuff to those sorts of things to the industry. So we essentially supply electric mini grids for these companies that can sit a mile down on the ocean floor. That's a harsh environment, and so there's a lot of interesting science and engineering questions connected with that, as you can, I'm sure, understand. This is usually one of the GE businesses that people have a lot of interest in because it's going very well. It's very popular these days. GE is by far the largest wind power maker, producer in the US, but we are just one of 5 very large suppliers globally. We have produced more than 50 gigawatts of onshore wind turbines across the globe. That's about 30,000 GE machines present in around 35 countries as of April this year, and I'm sure it's up from that at this point. So it's a very big business, and we've been spending a lot of effort trying to improve this. And so I'll say a little bit about it since people tend to be somewhat interested in this area. You have to do a lot of things to get this business to work right. People are usually interested in the generator, of course, but there are a lot of other things that are important. These blades are getting to be larger than 747s in the large wind turbines that people want to have these days. The towers are subjected to very interesting loads, and the foundations of the towers are another interesting area of endeavor. The electrical system, of course, after all, the purpose is to make electricity. You've got to bring the electricity down and get it out into the grid. That's an interesting area of work. You've got to design all this stuff, and then there's a lot of data associated with this to do it well, and I'll say a little more about that as we go. In fact, the controls for these systems has turned out to be one of the hottest topics that we've been working in. The wind blows when the wind blows, and the wind, as you know, can get gusty. It can get rather destructive. You're out here where there are more tornadoes than where we are. We're out where there are more hurricanes than yours, but there are a lot of wind events that can be destructive, and you do not want your wind tower to be lost in such events. So you usually design the system, of course, to stand up for those. And so we've spent a lot of effort on controls for extreme event monitoring and control. And that means that if we do this well, you can allow the wind turbine to run in more extreme events and deliver electricity to you. And we've actually had a lot of success improving the efficiency of these wind farms by doing the controls for the farms better and better. And we're still working on that a lot. Some sub-areas of that, you can imagine you put a lot of, you usually don't put up just one wind turbine, you usually put up several on a farm. There can in fact be hundreds. And wake management is a problem. You know, one, depending on the way the wind's blowing, what one turbine's doing is affecting, it's got a wake, it's affecting the turbine behind it. If you don't take that into account well and understand it well and set the controls to deliver at maximum efficiency, you're going to have a farm operating at subpar efficiency. So wake management is part of and understanding it and measuring it is an important thing we have to do with the control system. Noise management, these things do make some noise, and there are getting to be regulations on that. And so we have a lot of work on how you design these blades to lower the noise put out by the turbines, especially where they get close to where people live. Cooperative controls, if a turbine goes down for some reason, you want the farm to still operate efficiently. So each turbine has to know what every other turbine's condition is in the farm in order to make the entire farm operate well. So that's a cooperative software venture and control venture between all the turbines in a given farm. That has a lot of work behind that. And then finally, if I've got hundreds of turbines in a farm and they're all producing data because there are sensors on all these things, you want to keep a record of this stuff. You want to use it to optimize the efficiency of your farm. You want to use it to do condition-based maintenance, know when you have to go in and service a particular turbine, and the turbines are not all operating the same, so the required maintenance period is not the same on each of the turbines. You have to collect all that data coming in every millisecond from every turbine in the fleet somewhere and analyze all the stuff to get those kinds of answers. And so That's big data, and we do collect it, and we send it up to the cloud. Of course, it's not a real cloud, you know. We send it up to the cloud, and this is some nice guy's way of predicting it. But GE has made a bit, and I'll say more about this in a minute, but GE has gone big time into building up the software necessary to handle big data from big equipment systems, get it stored, get it analyzed, and make it useful. And they've built a platform, a software platform, which is GE can use. It's an open source platform, so anyone can use it. GE's building it, mostly at our software center in San Ramon, California. That's handling this problem. But this is one example of this kind of problem. You know, I can stand here and talk for a long time naming other examples. Every airline has a fleet of planes. All those planes have a lot of sensors on them. They're all dumping information continuously. You'd like to know when to go in and service the engines on those planes properly. You've got to take all the data coming off. Different pilots fly the planes different ways. You've got to know how it's being flown, what conditions it's being flown in, to make those kinds of decisions. And so you've got all this data dumping all the time off of a fleet of planes, and you've got to do the same sort of thing. And you can get a lot of other examples. And so this is giving rise to the so-called, I'll continue talking over this at the moment, to the so-called Internet of Things I'll say more about. And that's projected to be much larger than the internet we're all familiar with in terms of size and data it has to handle. And so GE spending a lot of effort trying to sort of become a software company enough to deal with this fact for the future. Everything, all these machines are going to have sensors and are going to be letting out data you're going to want to analyze, deal with properly, and use it to get higher efficiencies in the machines. This is the other area, of course, in renewable energy that GE works in. Now, we do not come to your house and put solar on your roof. There are other companies that will do that at the smaller scale. We deal with large-scale stuff, like if a utility wants a solar farm that produces many megawatts, we'll do that. And of course, that involves a lot of interesting questions, and I've listed some of them here. I won't bother to go into all these kinds of details, but there are a lot of things you have to do well to get a solar farm to work well. This is one of the things we make in connection with that, and that is, you know, solar cells, of course, produce DC. Your grid is AC. You've got to get it all converted properly and out onto the grid. We produce the inverters that do that and the control systems that are associated with them. This is an example of a first 1500 volt system that was built using silicon IGBTs. And that has been very popular for a while for these large solar farms. But we just introduced, I think about a week and a half ago, a silicon carbide version, which is about 1% more efficient, reduces the footprint, and it's more reliable. And so this is the latest version of that we're selling. And I'll say more about silicon carbide and wide bandgap devices in a moment. We also pay a lot of attention to the controls you have to put on these farms. When you start hanging all of these new generation sources that the utilities haven't seen before on the grid, they can cause problems. First of all, the things we used to put on the grid, we controlled. We told it when to turn on, when to turn off, when to dump electricity onto the grid, when not to. It was all under our control. The wind blows when the wind blows. The sun does not shine at night. In fact, it doesn't shine well during the day in certain cloud and storm conditions. And so all the time it's doing this to the grid, and the grid was not built for that. And so building control systems, SCADA systems that can deal with the transient nature of all these renewables that we all want to put on the grid is difficult. We've got a lot of work in that area. This is talking about some of the things we're doing for the solar problem, where things go up and down a lot due to clouds. In fact, we actually tune into weather stations in some of these and try to predict when the clouds are going to go over the farm, because it's helpful to know that. So sort of a prediction of what's going to happen to your particular solar farm. And we build a lot of control systems connected with dealing with these transients and with the connections to the system, to the overall grid system. So this I actually have already spoken about several times, and this is the point that industrial equipment is going to become smarter and smarter from the point of view of the sensors that are on them and the data that they are able to deliver to you. That's to the benefit of all of us because it'll improve the efficiency of the machines. It'll let us do condition-based maintenance. The machine will tell us when it's got a problem and when someone needs to come look at it. But you have to get all the right information. You have to collect it all. You have to look at it. You have to analyze it with the right algorithms and then send someone out or change the control system to accommodate what's happening out there. And so the control system, if you will, which I'll say more about later, is part of this whole Internet of Things because it's where you link all the software, all the data analysis, the cloud, if you will, to the actual operation of the machines on the ground. And as I said, GE's spending a lot of effort on this area, and as are a lot of other companies. In fact, there's an industrial internet consortium that was started in 2014 by 5 companies. I think they were AT&T, Cisco, GE, IBM, and what was the 5th one? Intel was the 5th one. And now it's, in that length of time, it's got like 250 members. Anyone can join, by the way, and it's to deal with fundamental general issues, non-competitive issues that come up in this data engorgement and dealing with the big data that's going to happen in the future. It's happening now and will happen more in the future. This is a prediction that there is an $8.6 trillion opportunity in productivity gains worldwide from what's going to happen in the Internet of Things in the future. The digital twin is a favorite GE name for the fact that probably every major piece of industrial equipment is going to have residing somewhere on some software system a software model of it, which is continuously being updated by the sensor information coming in from the real piece of equipment. And then you can take the model, the digital model of that piece of equipment, and use it for analysis and prediction of what's going to happen to the real equipment, and thereby reduce the downtime in the equipment, maintain it more efficiently, and so forth. Now I'm going to focus a little more on the GE's electrical parts. After all, it is still called General Electric. So these are areas that we are seeing changes in the electrical area. We're seeing increasing power demand on older grids, like especially in the US. Power demands do go up every year, and so the aging of the grid is a problem. People would like to increase power densities generally. Things are going into more harsh operating environments. I certainly showed you one example on the seafloor. Thermal management's always an issue in electrical equipment. People are doing more electric architectures. Of course, you can see that just driving around on the roads. And electric transportation and propulsion is an example of those electric architectures. Renewable, distributed, and transient generation, I've mentioned that in connection with the renewables. Higher speeds and frequencies, higher DVDTs, DIDTs, and electrical equipment, we're seeing a lot of that. And we're seeing a lot more electrical equipment being used in the healthcare industry too in connection with personalized medicine. Devices and packaging, GE uses devices and packaging of those devices in practically all of its businesses. We're seeing trends there. More miniaturization is desired in many cases. We're seeing higher voltages, higher temperatures arise, harsh environments, I've mentioned that. We're seeing a lot of embedded sensing and a lot of wireless interconnection taking place, increases in that. And people would like to see lower power dissipation, especially in connection with thermal management problems. This is just one quick example for you. I'll show a couple of these in the thermal management area. That's always an issue in electronic equipment, especially power equipment. It can be a limiting factor in what you can do. This is a problem with what we call the thermal management technologies where we're using nanosprings, and I see that For some reason, one of the words has decided to shift position. But what the problem is in a lot of power modules is that the silicon dies have a different thermal expansivity than their heat sinks, which tend to be metal. And after a while, you wind up with the big problems at the interface. So that can be a life-limiting problem. So what we developed here was what we call copper nanosprings. It's what it looks like, it's copper springs, basically. Actually, it's copper and tungsten. They connect the silicon die to the heat sink, and it turns out that they are three times stronger than bulk copper in this position, and that you can get a 10 times improvement in thermal resistivity relative to the standard state-of-the-art values by using something like this. So that was an improvement that we've worked on recently. Another one is what we call the thermal ground plane technology. Here, you have some very hot chips, for some reason, producing a lot of heat. You put them on a substrate like this, where it's got a material here that acts like a heat pipe. It gets vaporized at this end, it goes to the other end, and then you can take it out in the large area over here to some other medium, some other cooling device. So this is like a small heat pipe you can put as the substrate for electronic devices that are putting out a lot of heat. And it turns out that this thermal ground plane technology, that convection basically beats conduction. These convective techniques, you can beat any of the other substrates we've been able to produce, including diamond substrates. We do work in the MEMS area. We use MEMS switches where galvanic isolation is required, for instance. As you know, semiconductor switches leak, and so they aren't galvanically isolated, but MEMS switches can be. We also use them in resonators and in some gyroscopic applications. Piezoelectrics, we do a lot of work in that area because ultrasound business, and we mostly use PZT, lead zirconate titanate there, but we've looked at a number of other materials as well. Very important area. Ultrasound has really gone forward well in the healthcare area. Getting now into the wide bandgap area, there's certainly a very new push in power devices, and GE is in the power device area. We're not in the signal chips, we're into power chips. And what we are looking at mostly is silicon carbide. Silicon carbide is a favorite because we think it wins generally when you consider all of these factors. All of these higher bandgap devices have a better breakdown field. Silicon carbide has the best thermal conductivity. Of course, you can run things at higher temperatures with wide bandgap devices because the intrinsic carrier concentrations are down at a given temperature. So you can look at the progress that's happened in this area. A lot of people are getting into the silicon carbide area. If you compare a 1200 volt silicon carbide MOSFET versus a silicon IGBT in the same range, you can get 3 times lower switching losses, 2 times lower conduction losses, and about 50 degrees higher operating temperature with the silicon carbide device, and all of that can give you a lot of benefit in the system. You can also get 100 times higher switching frequencies with silicon carbide devices. So we've been putting a lot of effort into this and are actually building a fab cooperatively in the state of New York right now for silicon carbide devices. This is another one that's a little further out, in other words, more into the future. But you guys know, of course, that tubes went away because of what my former thesis advisor did, because of the transistor being invented. But, and all the subsequent developments in solid state, which has been very successful. However, tubes never went away in power RF. They never lost to solid state there, although you certainly can do it. If you have a microwave oven, and I'm sure there are several billion on the planet, I think I have 2 at home, every one of those has a tube in it, a magnetron. We can make those microwaves using gallium arsenide solid-state devices, but it would be much more expensive and no more reliable. Microwave ovens are very cheap. They win. Tubes win. And that's generally true of the final stages in TV stations, radio stations, most radars, most high-power RF, thyrotrons and accelerators. they're tubes. So tubes never lost a solid state in RF. What we're trying here is an experiment, a lot of thinking using tubes, and we build a lot of tubes for X-ray, our X-ray equipment. So we know something about building tubes. We're trying to see whether or not one can push down the success that tubes have continued to have in RF power applications to high power applications at 50 or 60 hertz. How far down in frequency can you push it? If that's the case, it could be of great assistance in grid applications like the massive conversion of AC to DC, as occurs in long-distance transmission in grids. So this is an experiment. We don't know how far this is going to go, but that's the idea here. And we're using plasma tubes that are somewhat similar to thyrotrons, but they're different. Power electronics in general, we're seeing trends there toward higher power and frequencies, larger scale power electronic systems, and we're seeing a lot more DC in use everywhere. A lot of lighting requires DC now. Your computer requires DC. Lots of DC applications that are making DC more popular. I'm not going to go back into the fight between Edison and Tesla on that, but we've forgiven each other for that one. Of course, there are a lot of interesting elements for in any power device. We've talked about the semiconductor devices. There are passives that are important. The control electronics for these devices are very important, and the packaging of the whole thing is very important. You have to get all that right. If you get it all right, you can get results like this with a wide bandgap inverter at 75 kilowatts. We've measured it. This is a standard industry one, and you get about 3 points of extra efficiency in that inverter made out of silicon carbide. In systems, we do work in the system as a whole. These, are continent-sized in the case of the main grids, of course, in the US and other developed countries, to mini grids. And these are present, of course, on planes, have grids, and GE does deal with those grids. Locomotives have grids, and I talked about grids at the bottom of the ocean. So mini grids or the maxi grids, we do a lot of work in those areas, and there's a lot of control efforts there. And once again, if you have sensors everywhere in a continent-sized grid and they're all producing data, another big data problem. Another example of a big data problem, optimizing large equipment like a big continent-sized grid. You've got a lot of data to deal with, and the Internet of Things is going to be the solution to things like that. Controls, I've already mentioned them, and so I'll just say quickly here that they are the edge of the Internet of Things. They're where you take all this data that you've analyzed so well and have decided what to do with it. You've got to ship it back down to something that actualizes motion, that actualizes something in reality. The control system is the interface to all of this data. So very important. We're doing a lot of work in that area in both the software in the controls and the hardware. They run on something, software doesn't sit there by itself. So we consider that a very important element in this so-called Internet of Things. Rotating electrical machines. Trends we're seeing there are changes from constant to variable speed. There's a lot more asynchronous generation now. Wind and solar are both asynchronous, but there are lots more asynchronous operation of motors and generators than there used to be. So the controls and the methods to deal with that is a change that's happening in rotating machinery. So we've been paying a lot of attention to that. Elimination of gears. People, if you can do that well with a variable speed drive and a motor, get rid of the gears, well, gears can break. So you can have a more reliable system. And of course, we use those in all sorts of GE businesses. And people usually ask me something about superconducting machines when I'm on machines, so I'll say a couple of things. This goes all the way back to the 1980 time frame when we were building some machines with low temperature superconductors. We built a couple of 20 MVA generators out of niobium titanium. It's doable. We did it. And this is a 3,000 horsepower DC homopolar motor that we built for the Navy, and they actually put it in a ship and drove a ship around in Chesapeake Bay with it. This is a particular machine we built with the Air Force that was a high-speed superconducting machine, over 10,000 RPM. It could actually produce several megawatts. This is a picture of it. That's about a meter across. And this was completed back around '07. We have designed a superconducting turbine you might use at very large power sizes for wind generation, although no one's ever built this. We haven't built it either, but we've thought about it. We've designed one. This is an example. One of our European groups has built another superconducting machine. They call this Genie. That was their name. It was built in Britain and France, and it had these characteristics. It was a slow-speed machine, slow-speed, high torque, and it was a hydro generator, and that's a picture of it. So it was built and it was load-tested over there, but not commercialized. None of these machines are commercial that I've showed you. We obviously know how to build them. The reason they're not commercial is fundamentally cost, economics, because they all have very good conventional competition with wound field machines, PM machines, all sorts of other standard technologies. And when you add it up, what these machines can do and their advantages, that does not overcome the price differential. So it's really an economic game at this point. When the superconducting parts become more available, then this will happen. More available at a lesser cost, this will be more doable. The reason we have a whole big business in MRI, which is all superconducting practically, is that you can't do it any other way. Try to make an MRI machine with a wound field piece of copper and you'll be using the nearest river to cool it. That's the problem. You just can't do it well with anything but superconducting technology. So that is why that business is superconducting and why it wins that way. Now, I always like to mention this as a topic because it's always important. If you're going to make anything electrical, I don't care what it is, insulation always has to be had. And it's considered, oh, just off the shelf, it's common stuff, you know, everybody can get insulation somewhere, but that's not always the case. Since people are continuously asking for higher temperatures, which will melt the insulation and mess your machine up, or they want higher heat transfer because they want the heat to go through the insulator, and they want, of course, the insulator's got to insulate electrically, but they want it to be a high thermal conductor. Oops, Wiedemann-Franz law, oops, that's the problem. And so trying to make materials that do that are hard. And they also want higher voltages. Voltages are tending to go up in a lot of equipment. So there's always problems to deal with in the installation area, and we do work in this area, and it's never a finished area of work. There's always something to do there, and they always want more. And so it's an important topic for anything you want to do that's electrical. This is another megatrend topic, and I know you guys have work in batteries here. Why is it getting to be very important? Well, I've listed three main areas here. In the transportation area, you can just go out and look at cars. I don't know how many hybrid cars you have in your lots here, probably a number, but we're using more and more in transportation for improved fuel economy, reduced emissions, enhanced performance. That's going to continue. That's a need for batteries there or something. And energy area, power quality, I mentioned the problems, transient problems that are being caused by the renewables. One of the solutions is to put storage online so that during peaks of delivery of power by a renewable energy source, you can store that and use it when there's a problem. So that's greatly desired here. And then finally, of course, there are more traditional uses for safety. Of course, every hospital's got a UPS, an uninterruptible power source. A lot of locations have to have something like that for safety and reliability, and the fact that you don't want your internet to go down and so forth when there is a problem. So a lot of reasons for this. I put this up here just to remind us that electric cars are not as new as sometimes we think they are when you go out and look in the parking lot. This is our founder with his electric car in 1913, and this is another rather famous guy in early stages of GE, Steinmetz, with his electric car in 1914. So, you know, the wheel turns. GE is probably the biggest manufacturer of the largest energy storage method that's currently used on the planet, and that's pumped hydro. Here you're pumping water up, and if you conveniently have a lake located at a high location, not far from the electric grid. And believe me, there aren't a lot of such great locations. But if you have one, you can pump water into the lake when you have extra power, and then take it out of the lake through the turbine and make hydropower when you need extra power. And so this is the main method today, and it works well. People are looking at a lot of other things. This is the standard Argonne plot where you plot energy density versus power density. Capacitor-type devices tend to work on the power density area. Batteries are better in the energy density area. People want to improve all of this. We've done some work ourselves on certain kinds of batteries, but at the moment, we're not solving the problem ourselves, but we're very interested in it. We're also looking at, in fact, trying to make a business in solid oxide fuel cells. Fuel cells are another area of interest in connection with storage and generation. There are a lot of hard problems, a lot of things you have to solve. You have to get these fuel cells to have long life and get the costs down. We're working on that right now. We're trying to build a factory, actually, for solid oxide fuel cells as we speak. So we'll see how that goes. It could be another great power source. So I'm basically through, and I think I've left a few minutes for questions. This is a slide where just personal thoughts about other things that might be coming up in the future, interesting to work on. And as Peter's already mentioned, there is Peter, number one, HTS wires. So everyone wants that, and they're too expensive now and not high enough quality yet. New signal electronics to bypass the coming events with Moore's law, going to be shut down by certain laws of physics, and people think about things like that. Better power electronics, we've already talked about emerging materials there. There's never going to be an end to people wanting new and better materials in many, many, many areas. So I just list it that way, and with a long list. More efficient, cheaper, and better electrical generation by any method. Better manufacturing methods, we've talked about additive. And by the way, additive is bringing a lot of manufacturing back into the US. Robotics and automation is going to be a big deal. We are working in that area. Bioelectronic interfaces, that's going to be a big deal. Smart prosthetics can be, of course, of great service to a number of humans who have disabilities. Sensors of all sorts, always important. Better computers, and I put quantum. I'm not sure, I'm not going to get into things like D-Wave. Software, naturally, is going to be more and more important, and I mentioned the Internet of Things. So those are just some thoughts, and your thoughts about that are as good as mine, but that's some things I think are going to be of interest in the future. So I am finished with what I wanted to say, and so if anyone has a question, feel free.
Thank you for coming. This is a very interesting talk. Even GE can't make everything that it needs, so you've got a supply chain both within your company as well as with your vendors and suppliers. I'm interested in how you, as the head of the R&D arm, interface with the entire supply chain, both to push out the technologies that you're developing as well as to understand what kinds of things they're grappling with. I don't have anything more specific than that, but I imagine that the information flow is something that you need to manage in some way.
Well, you've hit on an area in supply chain that one could probably talk for hours about, because it's a constant question, how to improve that, how to deal with that, how to get it better. We have a global supply chain. And so there are all sorts of issues to deal with. And you can think not only of the equipment and material supply chain, but the knowledge supply chain, of which you guys are part. I've already mentioned that, how your organization helps us. But we work with a lot of universities and other national labs as well in the knowledge supply chain. I mean, we're working at the forefront of knowledge in a lot of areas in what we're trying to do. The knowledge supply chain is very important, and I'm a bit more familiar with that part of the problem in the R&D center, because we have a lot of the connections with Argonne and with all of our other partners from the R&D center itself. We have specialists in the problems associated with dealing with suppliers of the materials, components, and equipment that we need. Very difficult problem. We're constantly dealing with that. We're trying to treat many key suppliers as partners, not just as suppliers. You always want to have more than one supplier for anything, because you can get in big trouble if that supplier has a problem if you only have one. So there are certain basic rules like that you try to obey. You try to make key suppliers part of your enterprise in the sense of a partnership, and you help them solve problems. We occasionally send R&D people and engineers to suppliers who are having a problem and help them solve the problem, because we have to have what they're making. You said it, I mean, we can only make a small fraction of all the things that go into all the things I just showed you. So that's a short answer to what's a very complicated question.
I think that all of this stuff you showed us was really interesting. I was interested in how you use all of those engineers and R&D people globally to get those things done. Is it all done locally, or do you actually spread the wealth and spread that knowledge when you're developing these things?
Yes. That also could be a very long answer, because as you see, we have a lot of global locations. But in general, our GE operates literally in every country. And so Europe will have different demands than North America or South America. Will be developing its technology, and it will have different needs in those different parts of the world. So the first division of labor that we think about in these different sites is the European Center, which is in Munich, will understand thoroughly the problems of the EU, of the European Union. And I'm not talking about Brexit or anything like that. I'm talking about technical problems. But they will thoroughly understand that and will focus their efforts toward things that are of more interest in the way Europe's pushing their technologies. The same goes for the Shanghai group in China, the India group, the Rio group for South America, and so forth. So the group in Saudi Arabia is specifically trying to help with problems. You can imagine they have oil and gas problems of all sorts in countries in that area. So they're very focused in that particular set of technologies there. So that's the first way we divide up the labor according to the needs of that part of the globe and how they're developing. So that sort of sets how the different groups will operate. But beyond that, there are things that, of course, are global. And so we have communication methods, we have linkages, we have internal conferences that bring everybody together periodically to talk about common problems, because there are obviously issues. I mean, for instance, everybody wants wind power, everybody wants solar in the world today. All the people involved with that talk together, and different countries may be developing it differently with different regulations or with different feed-in tariffs, for instance. So that has to be taken into account. But there are a lot of problems with commonality, and we have a lot of communication methods that let people in one area talk to another and benefit from people thinking in another area. So a good idea can come from anywhere.
So you mentioned that you collaborate with national labs. So which one of those national labs you can say they are the most, the biggest partner in terms of money you put in that lab? And what should the national lab do to attract more, not only you come and use our facilities, but actually your funding as well?
You're trying to get me in trouble.
She's trying to get me in trouble.
Oh, is that right? I honestly do not know which national lab we use the most. We use yours a lot, as I said. In fact, I do know that of all the high-performance computing clusters that are available, we use yours the most. I do know that. I just happen to know that because I know the guy who's in charge of that at our R&D center. But we also have had a lot of interactions with Oak Ridge. We've had interactions with Sandia. Some with Los Alamos and Livermore, but less with those. As you know, those labs have a lot of concentration in certain other kinds of things, classified areas. But we commonly look to all of these labs for problems where we might get some help. And so it's been very useful over the years. And so I honestly can't give you a number for which one is number one, except you guys are pretty close if you're not number one.
We can do us. Two related questions. You described something from discovery to product, which can be a 20-year cycle, and patent life is 18 years. How do you manage IP when your product cycle is longer than life of patents? And I know that that would be a challenge. And then specifically on water, which I work on, we have ultimate infrastructure projects. The volumes of water are infinitely larger than petroleum. And it's a very conservative, very risk-averse industry, but you're a leader there. How do you make decisions on when you're going to invest in water technologies and how you're going to get into the marketplace when we may have a 40-year cycle on deploying water technologies?
Yeah, that's a lot of, you guys ask very questions that deserve very detailed answers, all of you. The way we deal with very long cycle things, like for instance the ceramics development I showed you that took 25 years to get recently into jet engines, and the IP, which doesn't last as long, is that continuously during that cycle new IP is being invented. We do not solve, of course there are some base patents that start out, but during that entire cycle new things are coming up, because there are constantly problems that are being solved in connection with making these things worthwhile or usable in those applications. So you will always, when you get to the end point, have operable patents. Yes, you'll have probably some from the beginning that have run out, but at least it constitutes a publication, and at least no one else can patent that because it's out there as a publication, so it's then public information. But yes, because there's a continuous output of patents in this 25-year learning process, you will always at the end have some to help you. Specifically for water, yes, there's a lot of great conservatism in that industry, and so they're constantly thinking about how to break into conservative areas of that, and actually that's a discussion within the company, what to do there. One of the just demographic factors that makes GE think that is a good place to be and to maintain good ability is just the world demographics. I mean, you know, we're at 7.1 billion, we're going to 10 relatively soon, and a lot of people don't have water. Something's got to be done about it. So we sell desalinization technology, for instance, and we have a lot of work trying to make that more efficient and less costly. So we think that the nature of demographics in the world is going to force a lot more attention to water on the planet, and we want to be ready when that happens. Exactly what the nexus points are, I don't know, but that's one of the attitudes being taken in that business.
Let's just take a couple more questions. One back there.
Back here, other side. All right. So one of the successes of the semiconductor industry is sort of an information transfer to basic research and the roadmap outlining not only switching speed or something like that, but also manufacturing constraints. You know, this process, whatever it is, magically needs to be under a certain temperature, et cetera. Maybe using your superconducting endeavors or anything you want, how can other fields duplicate that communication to basic research that wants to have at least a chance to succeed to fill those holes in these emerging technologies?
Well, I can give you one answer to that. Yeah, I agree with you that there's been a great feedback within the semiconductor industry. All these hugely complicated and expensive chip fabs have benefited from a lot of feedback of information from the way the product behaves. That is one of the desires and purposes of this whole Internet of Things. If eventually we have what we like to call the digital, sometimes we call it the digital string. If we have the entire process of manufacturing, and I'm not just talking about chips now, of anything, any significant piece of equipment, under, let's say, digital control, under control of the Internet of Things, then we'll start out with a completely digital model. Already regular old blueprints, and like in the old days, are beginning to go away in favor of just 3D CAD models. That's what you're going to work with. It's not paper anymore. We're trying to force that in certain areas of GE business. So you start out with design that's all on the computer. It's all software. It's all in CAD systems. And then the manufacturing from that becomes much more automated. A lot of robotics and automation. You have a very automated factory at work for you there. You're capturing information at all of these stages. Finally, you build it, you go into testing, probably prototype testing. That's very well automated. That's information is captured there. Finally, go into production and use in the field. And you have digital twins for what's working out in the field. You learn from sensors on the machines exactly how they're operating. The idea is that you will have the feedback loop you're talking about ultimately in the Internet of Things on all the big equipment. So how are things working? Well, you know what you designed. You're not just going to go back and scratch your head again next time you're designing. You're going to have continuous feedback of information for how what you actually designed and went through the entire manufacturing and testing and delivery process to the consumer. That entire bit of information, oh, it didn't manufacture well because of this, the way you designed this, or it's failing in the field because of something, or its life isn't long enough. All of that information that's taken in the entire chain from design to building and selling and running it is available. It's stored in the cloud. We can analyze it and bring it back into the design process. And it'll improve not only the design process quickly and more efficiently, but the manufacturing process and the testing process. So that's ultimately the desire. It's going to take a while, obviously, to get all that to work. Like as you point out, the chip fab business has done that pretty well.
It's remarkably public. The goals for durability, performance, and all of those things. I think that's the collection of it in one place makes it public.
Yeah, and I think a lot of it will be public. Of course, there will be proprietary elements, naturally. Just as there are in, Intel isn't going to tell you how they're
let's take
designing their chip. But
One more question, then we. It's actually very fascinating, but I'm watching the time, so we got last one.
When regarding the help that that you're getting help national labs from with your R&D, do you often only use the laboratories for fundamental research, basic science problems, or are you also engaging with the labs to do some of your protected intellectual property work? And what do you look for in a national lab to help you protect that intellectual property if you do share it with them?
We do both. We've done both. And I think you guys have, for instance, I don't know the details, so you'll have to correct me, Peter, but I believe you have a different way of charging for the use of the APS when it's open research, basic research, if you will, question being answered versus a proprietary use of a beamline. And so, but we have done both. When we, for instance, have used your high-performance cluster, we've often used it in extremely difficult CFD calculations, computational fluid dynamics calculations, for the fluid flows, the air flows that are going on in jet engines and other such very difficult equipment. So sometimes that'll be proprietary. Sometimes it will not. So we've done both. We've used national labs both ways, and we pay if there's a tiered charging for that, we pay the extra fee if we need to use it for something that's proprietary. I think more often it's not been proprietary, but we've done both.
I mean, just to comment, I mean, as well as the use of the facilities, we do actually have relationships with you on, specific industrial projects where we're cooperating in research, to deliver particular technology. So that's done.
That's right.
We'd actually like to do more of it. So I very much like your list because we can pick some things off out of that and just do that. So with that, I thank you. That was a really tremendous tour, actually, through a great company. Very interesting to see what you're doing. It's very interesting to see the vision forward. A company that will actually look at technologies and imagine that it's going to take 25 years to deploy it, and we will do that. That's an inspiration because there aren't many businesses like that. And they're actually the kind of folks that we like to work with. So thank you so much.
Thank you.